The last conic section that we need to discuss is the hyperbola. So that's what this lesson is going to be about, the hyperbola. We have dealt with hyperbola previously when we did rational functions, but this is going to be a fairly different concept. So let's look at the definition. A hyperbola is the set of points p, x, y in a plane such that the absolute value of the difference between the distances from p to two fixed points, f1 and f2, called the foci, is a constant. Now you could read that definition again, like all the other definitions, a bunch of times, and it's not going to make a whole lot of sense. So let's look at these pictures to kind of make sense of them. There's two different types of hyperbola we're going to look at. One which we're going to call a horizontal hyperbola, that's this one, and the other one we'll call vertical, because that's kind of how the graphs line up. The red pieces are the actual graphs. And the idea is this. Here is some random point on my hyperbola. That point is a certain distance away from the foci. This is one foci, and that would be one distance. This is another foci, and that would be another distance. Let's call this D1 and D2. So if I look at that, if I take the absolute value of the difference between the distances, so if I do D1 minus D2, and I take the absolute value of that, whatever value I get out of that whole thing should be the same regardless of what point I choose. So I choose another point, say this point right here. I look at the distance that is from one point, the distance that is to the other point in terms of the foci. Call this, I don't know, D3 and D4. So if I take the difference between D3 and D4 and look at the absolute value, while D3 and D4 may be different than D1 and D2, the absolute value of their difference should be equal. This value here should be equal to this value here. And all the points for which that happens create my hyperbola. This piece here and this piece here. Now again, the definition is all great to know, and the definition is really based off distance, and that's kind of all our conic sections. The definitions are based off of distances. But really what you want to know is how to construct a hyperbola. So there's a couple of things. One is the center of the hyperbola. We're going to start off with the center of our hyperbola to be 0, 0. This is not actually a point on the graph at all, but that's sort of where this thing branches out from. There are two distances we're really going to discuss here. One is a horizontal and one is a vertical distance. These two distances are going to be based off of two axes that we're going to call the transverse and the conjugate axis. So let's look at the first one, which is the transverse axis. So this distance right here we'll label A, which makes this point right here to be called A, 0. And this distance here is also A. So this point right here would be negative A, 0. Those 2 points are called my vertices. Those are points on the hyperbola. This axis that goes from here to here, which total distance would be 2a, is called the transverse axis. It's an axis that goes really through the middle of the graph and cuts the graph into two equal pieces. One branch on one side of it, the other branch on the other side of it for both of these. Okay, so this is your transverse axis. So this graph is a horizontal transverse axis. Now there's two other values here that are going to be important too, and that's the vertical distances on this one, which will be b, which puts us at this point here, which is, b 0 comma b and 0 comma negative b. Now these are not points on my graph, but what happens is these points or these distances create this box, and this box isn't always going to be a square. Sometimes b is bigger, sometimes a is bigger. It's not like an ellipse where a always has to be the bigger value. It all depends on what distance is bigger. If b is bigger, you might get more of a rectangle here out of this box. If a is bigger, you might get a rectangle the other way. But this box is important. This box, which doesn't have an official name to it, but I like to call it the asymptote box, is really a definitive way of getting your graph. This graph really is shaped like a parabola, almost. And there's two of them, sort of placed across from one another. But those parabolas are approaching asymptotes. There's two slant asymptotes on either one, here and here. Those slant asymptotes really kind of define where my graph is. If I know where those asymptotes are and I know where my vertices are, This is starting to get sloppy now. Let me erase some of this. If I know where my asymptotes are, and I know where my vertices are, I can use those things to help construct my graph. So let me erase a little bit more. The idea is this. I can get those asymptotes by creating this box. By knowing what B and A are, I can create this box here. If I use the diagonals of the box, the diagonal should go through the center but also go through the corners of the box. Those diagonals are my asymptotes. If I then know where my vertices are, here and here, and I know my asymptotes are here and here, then all I have to do is make my graph approach that asymptote and approach that asymptote. Same thing here and here. So that A and B is pretty important. They create the asymptote box, but A also gets you your vertices. If you want to know the equation of the asymptotes, these are the equations of my two asymptotes, y equals negative b over ax or positive b over ax. The idea is b over a plus or minus. Once I have those values, I can construct my hyperbola. Now there's two other values here that are important, which are my foci. They're going to be based off of this value c. C is this distance off of my center, just like sort of the ellipse. The foci are always kind of inside the curve of the hyperbola. And I can find, as long as I can find c, I can find those values as well. This picture right here is a vertical hyperbola, same deal. This would be the transverse axis. It's now vertical. This would be what we call the conjugate axis. A is the distance on the transverse axis. B is the distance on the conjugate axis. A does not have to be bigger than B. Depending on which one's bigger will change kind of what your asymptote box looks like. Like here, B would be the bigger value if my box looked like this. And then the diagonals of that box create my asymptotes. The more different A and B are, sort of the more open or closed your curve's going to be. The more square your box is, kind of like this one is, the more, I should say, I guess the more normal your graph's going to look. But whether you have a vertical or transverse axis sort of just changes whether or not your graph is lined up across from one another vertically or horizontally. So let's look at some equations of a hyperbola. Alright, so here are some equations of hyperbola with center 0, 0. These equations look very, very similar to the equations of a ellipse. There's one major difference, the minus. So you need to be able to recognize the difference between a hyperbola, an ellipse, a circle, and a parabola. And if you can recognize the distance between those things, just in terms of the difference between those things, just in terms of their equations, you know, that's really a big goal. So if I said, alright, y equals x squared, you got to know that's a parabola. Why? Because only one of the variables squared. If I said x squared over 3 plus y squared over 3 equals 1, you'd tell me that's a circle. Why? Because both are squared. They're added together, and the things underneath are the same. If I said x squared over 4 plus y squared over 3 equals 1, you tell me an ellipse. Why? Both are squared. They're added together, but the radii underneath are different. And if I said x squared over 4 minus y squared over 3 equals 1, you'd have to tell me hyperbola. Why? Both are squared. There's a difference between them. Whether these two numbers are different or not really doesn't matter. They could be the same. They could both be 4. This would still be a hyperbola. It's just A and B are now the same. Remember, A does not have to be bigger than B in a hyperbola. A can be equal to B, A can be smaller than B, A can be bigger than B. Now, the idea is, okay, well then how do I know where to put A and what kind of hyperbola I have if I'm not really looking for the bigger number like I was with an ellipse? Well, it all depends on the order of the subtraction. A is always in the first part of the subtraction, and whether the x is in the first part or the y is in the first part of the subtraction tells you what kind of transverse axis you have. If x is in the front, then I have a horizontal transverse axis, and my graph will be horizontally across from one another. If y is in the front of the subtraction, then I have a vertical transverse axis, and my graph would be vertically across from one another. A would always be the one under the first variable, whether it's x or y. And that's how you can sort of figure these ones out. Your asymptotes for each are either b over a or a over b, plus or minus, because there's two of them. That depends on what kind of transverse axis you have. The length of the transverse is 2a, the length of the conjugate is 2b, and your foci are based off of c. Now this equation is a little different than before. A squared plus b squared equals c squared. This one is the Pythagorean theorem, as opposed to the ellipse, which was minus b squared. So let's look at a question. So, find the coordinates of the foci, find the lengths of the transverse and conjugate axis, and find the equations of the asymptotes for this particular graph. Well, one, this isn't in the form we want, right? All these things need to be equal to 1. So if I divide by 9, I get x squared over 9 minus y squared over 1 equals 1. Now, this is going to be a hyperbola. It's going to be a horizontal hyperbola because x is first. So that tells me that a squared equals 9 and b squared equals 1. So a equals 3 and b equals 1. So the transverse is 2a, so that's going to be 6. The conjugate is 2b, so that's going to be 2. Those are the lengths of the transverse and the conjugate axis. The asymptotes, if my x is first and I have a horizontal transverse axis, is y equals plus or minus b over a, that's 1 over 3x. The foci is based off of a squared plus b squared equals c squared. In that case, I'm going to get 9 plus 1 equals c squared, so c equals plus or minus the square root of 10. Now, it said coordinates. If I have a horizontal transverse axis, these are x values, and the y values are 0, so those are my foci. And then if it asks me to graph it, well, if I'm going to graph it, I'd say, alright, well, I got a horizontal distance of 3, a vertical distance of 1, and this is my A here, this is my B here. So there's my vertices. Here is my asymptote box. The diagonals of this box are my slant asymptotes. They should go straight through the center. And then since my graph is horizontal, then I start at this vertex, this vertex, and I approach this asymptote, then I approach this asymptote. Same thing here. I approach this asymptote, and I approach this asymptote. This point is negative 3, 0. This point is 3, 0. And that's it. There's your graph. That's the graph of the hyperbola. Here's another question. Find the coordinates of the foci, find the lengths of the transverse and the conjugate axis, and find the equations of the asymptotes for this particular one. So again, got to be equal to 1. So if I divide by 100 across the board, I'm going to get y squared over 25 minus x squared over 4 equals 1. Y is first, so that tells me this is my a now, or in this case a squared. So a squared equals 25, b squared equals 4, so a equals 5, b equals 2. My transverse is 2a, so 10. My conjugate is 2b, so that's 4. What else do we need? We need the asymptotes. So when we have a y squared first, which means we have a vertical transverse axis, your asymptote is a over bx. So I'm going to say it's y equals plus or minus a over b, so 5 over 2x. Those are the equations of my asymptotes. My foci are going to be a squared plus b squared equals c squared. So in that case we're going to get, what, 25 plus 4 equals c squared, so c equals plus or minus square root of 29. Now we have a vertical, right? This is vertical transverse axis. The transverse axis goes this way. My graph looks like this. My foci are in here. My foci are on the y-axis, so these are y values. So my coordinates are going to be 0, comma, plus or minus square root of 29 as my foci. Now if I wanted to graph this thing, it's again not hard. The vertical distance, which is a now, is going to be 5. The horizontal distance is going to be 2. That's the conjugate axis. That's the transverse axis. I make this box, which is more of a rectangular shape because those numbers are a little further away from one another. The diagonals of that box are my asymptotes. This point right here is a vertex. This point right here is a vertex, and I approach my asymptotes. In this case, I'm going to lose room in the bottom, but that's basically what my hyperbola is going to look like. One more. Find the equation of the hyperbola with vertical transverse axis centered at the origin, and length of the transverse is 16, length of the conjugate's 24. So right away it says the equation of the hyperbola that has a vertical transverse axis and centered at the origin. Well, if it's a vertical transverse axis, y squared has to be first. So this is the form that we're looking for. This is centered at the origin. Y squared being first gives me a vertical transverse axis. All we need to know is what a and b are, and we're done. So the length of the transverse is 16, so that tells me that 2a equals 16, so a equals 8. And the length of the conjugate is 24. Well, that's 2b. 2b equals 24, so that tells me b equals 12. So I plug those in here and here, and I get y squared over 12 squared, or y squared over 8 squared, minus x squared over 12 squared equals 1, or y squared over 64 minus x squared over 144 equals 1. That's the equation of my hyperbola. So same kind of question as before, but this one you have to construct the equation. So that's pretty much it for hyperbolas. What you really want to focus on is learning these equations and recognizing whether or not you have a hyperbola, an ellipse, a circle, or parabola. And once you learn which one you have, what information can you pull out of the equation? What form is it in? Is the y first? Is the x first? Is the bigger number under the y? Is the bigger number under the x? It depends on what you're looking for, ellipse, hyperbola. And then what does that information mean? A and b are distances for all of these. What distances? What do those distances represent in the graphs? These are the things you want to get comfortable with. Because what we're going to do next is we're going to take these conic sections and we're not going to have them centered at the origin anymore. So we're going to move the center somewhere else on the xy plane. But if I'm doing a hyperbola and my center isn't here, but let's say my center is over here, as long as I know how far to go in each direction, A and B, to create my asymptote box, I can always connect the diagonals. If it's horizontal, those are my vertices, and this is what my graph's going to look like. Now, it's not centered at the origin, which would be here. It's centered over here, but it's really constructed the same way, as long as I know where the center is. So you really want to get comfortable with all these values and how to construct it so that when we move the center, the only thing that's going to change is the center and nothing else. All the other values represent the exact same thing.